This is a demo of the Failure Congestion Risk Modeler tool, which is a part of the Planning and Optimization function pack supporting the WAN Automation Engine platform. The Failure Congestion Risk Modeler is a tool that can be used within WAE design to calculate the risk of circuit congestion due to any single failure scenario in the network. Congestion risk in this case is the combination of two other factors, including the likelihood of a failure scenario occurring, as well as the consequences or severity of that failure scenario on your network. By combining these two factors into an overall risk metric, we're better able to differentiate between failures that are more severe but are less likely from those that are more likely but result in less congestion on your network, thus allowing for more targeted upgrades in your network where they are most needed to address potential failures. Included in the tool bundle is documentation to fully describe the overall functionality of the tool, including the expected input parameters and output results, as well as a sample plan file to further demonstrate the use of the tool, as well as how to interpret the output report produced from the tool. So I'll be going through a typical use case where this tool might be used during a planning exercise to help determine where best to upgrade your network to account for potential congestion caused by failure scenarios in your network. Typically this is done using WAE design through the use of simulation analysis. Here I've got open the plan file that is bundled with the tool. It's a modified US WAN with both layer 3 and underlying layer 1 network. The first step normally in this type of use case is to run the simulation analysis to determine if any failure scenarios in the network will cause congestion in my network. I will select failures including circuits, nodes, and L1 links in this case, and we'll let the simulation analysis run to determine the worst case analysis. So this runs fairly quickly, and what we can see from that is some worst case utilization in the network as a result of failures. So the worst case data here gives us an idea of how many circuits in my network have the potential for congesting due to some failure in the network. And we can see here, if we use a 90% utilization as the threshold for congestion, we have about 16 circuits that have the potential for congesting due to some failure in the network. And this is important information to begin the planning process. What the Failure Congestion Risk Modeler does is broaden that and provide additional information to help determine how likely each of these circuits are to congest. Not only that there is some failure that could cause them to congest at these levels, but how many failures cause them to congest, as well as the likelihood of those failures. And in addition to that, what is the consequences of those failures, the severity of congestion for each of these failures. And with all this information together, we can derive an overall risk to your network for each of these circuits to congest. And this information can be used to help determine where best to upgrade your network. If, for example, you can't upgrade all 16 of these circuits, this additional information provided by the Failure Congestion Risk Modeler can help determine where you can place your more limited resources and where those resources can be applied to your network to best address the upgrades in your network based on your what's important to your requirements. Okay, so let's go ahead and start up the Failure Congestion Risk Modeler and run it on this plan file so we can take a closer look at the results. If we start up the tool, we'll see a user interface that allows us to enter the required input options. One of the most important input options is the relative failure weight applied to each of the object types that will be considered in the failure scenarios for this tool. The tool currently supports 4 object types for failures, including circuits, nodes, SRLGs, and L1 links. So in order to determine the likelihood of these failures and the results of those failures in the network, we need to set a particular factor here that we call the relative failure weight. And what this is a sort of a relative likelihood for this particular object or object type to fail as compared to other objects either of that type or of different types. And this weight is anywhere between 0 and 1, and we can set that in a number of ways. One way we can do that is through this initialization tab, and what this does is it basically you can run this in the initialized weights mode only, and what this will do is it will add user columns to your plan file that will then be populated by the weights that you've assigned in this tab. So these weights, that, as I said, determine the relative likelihood of failures of these particular object types. So for example, let's say we know based on historical data that circuit failures are twice as likely to occur as L1 link failures. So we can go in and assign this one, let's say, a weight of 0.5, and our L1 link weights will assign a 0.25. So we'll make this circuits have a weight of twice the weight of the L1 links. And then we know that based on historical data that node failures are relatively rare. They occur, let's say, on the order of a tenth of as often as circuit failures. So we'll go in and put that as a 0.05, and we'll leave SRLG failure weights alone. In this demo, we won't be considering SRLG failures. So if we go in and select the initialized weights only and we run that, it will basically go in and add, as I said, add those user columns in, and we'll take a look at that and see the results of those. So if we look at, for example, nodes, the nodes table, we can see it added a user column, FCRM, fail weight. So that will be used, these are the values that will be used in the derivation of the risk associated with those objects failing. So once we have this user column in place, initialized with the value we provided for a particular object type representing the weight, the failure weight for that object type, we then can go, if we choose, and provide more granularity and differentiate between objects of a particular type. So let's say, for example, in this case, we know that the optical provider that we have for in and around Washington DC connectivity is more likely to fail than other optical fibers that are provided by other providers. So if we go and filter on those links in and around the Washington DC hub, we can bring those up and we can change those failure weights. Right now they're at 0.25, so if we go and double click on those, we can tweak those values and bump those up. Let's say they're 0.4 instead. So we'll add those, put those in, and now if we show all of them, we'll see that some of those have the 0.4, some have the 0.25, representing different relative likelihoods that those will fail. Okay, so once we have all of the weights in place and we've tweaked those as we wish to differentiate between different objects and different object types, we then can go back to the tool itself. So we'll bring back up the tool, and let's talk about some of the other options we provide here. So the threshold utilization is an option that determines what utilization level is determined to be congestion. So in this case, we'll put in, let's say, 90%. That represents congestion in this case, and any failure that results in 90% or more congestion on a particular circuit will be considered in the derivation. We can also set the number of parallel processes here just to speed things up if you have a multi-processing platform that you're using. So we'll go ahead and set that up to 8. Here you can set the particular traffic level that is being considered. And we can also change the default add-on values. If we want to run this tool multiple times, we can use the current selection as the defaults, and then next time you run the tool, all of the current selections will be defaulted and you won't have to go and change those every time you run it. So that just makes it a little easier to run many times. Okay, so once we have those options set, we then can go and set the failure scenarios considered. So here we'll go and set the nodes, circuits, and L1 links. And we won't use the initialization tab here because we've already initialized all of our failure weights in the previous step. So we'll just leave that tab alone. Alright, so we'll go ahead and run that. So what we're going to get here from the output is a report. So this report will have a summary. So we'll look at that first. So the summary basically just reiterates some of the options you selected, including the threshold utilization, which is we saw earlier was 90%. It tells you the failure scenarios included, in this case nodes, circuits, and L1 links. And then it gives you a high level indication of the number of circuits and interfaces that resulted in non-zero risk of congestion due to some failure in the network. So if we can see here, we see that there were 9 circuits and 16 interfaces that had some risk of being congested due to some failure in the network. We also have, in addition to the summary, some more detailed results, and we'll take a look at that now. The first one is a report detailing the circuit congestion results. So here we have all of the circuits that had some non-zero risk of congestion due to one or more failures in the network. The first 4 columns just give you a definition of the particular circuit that is indicated. The congestion likelihood metric, this is a overall likelihood that a metric that indicates the overall likelihood that this particular circuit will congest due to some individual failure in the network. So this gives you an idea of which circuits are most likely to congest due to some failure in the network. And so if we can go in and sort on those and see that particular circuits are more likely to congest and those that are less likely. Next is a risk metric. So this takes not only the likelihood, so this particular metric that we just talked about, as well as the consequences of those failures. So in this case, the consequences represent the severity of the congestion or the amount of traffic that's over and above this 90% threshold that you've set and defined as congestion. So if we combine those two, we get an overall risk metric which represents the severity or the risk of congesting of this particular circuit. So we can sort on either of these and determine which of our circuits are either most likely or represent the highest risk. In addition to that, we have some additional factors, so including the number of circuits that failed resulting in congestion on this particular circuit, number of nodes, as well as the number of L1 links. And if we had considered SRLGs, that would be another column indicated here. In addition to those, we also have the failures that are the highest likelihood resulting in congestion on this network. So these circuits, these objects, and it could be any of the objects we considered, these are the ones that are most likely to fail and cause congestion on your network. And then finally we have those that produce the highest risk. So the ones that produce not only the highest likelihood, but if you combine that with the consequences that they produce, the amount of traffic over this threshold utilization, this represents the failure that is the highest risk, poses the highest risk for congestion on this particular circuit. So with this information, we can clearly, we can sort on those and see which represents the most likely, which is the highest risk, and it gives you more information about where you might want to apply your upgrades in your network. You can also look at more detail if we go and look at the interface congestion report. Here we can see more information about each side of the particular circuits that we just we're looking at in the circuit congestion report. We can look at each side of that separately, and it has similar information. Okay, so then if we want to go investigate a little more closely, let's say we want to look at the 5 highest risk circuits for congesting those in the network. We'll highlight those in the report, filter on those, and it brings those circuits up in your circuits table. So we can see those highlighted here, and these represent the circuits that are at the highest risk for congesting in the network due to some failure. This concludes the demo of the Failure Congestion Risk Modeler tool. For more information, please consult the documentation or send questions to the WAE Function Pack Help email list. Thank you.